What is this thing we're trying to do? It's a series of true statements. By the way, this is my definition. Used to prove that a larger statement is true. Is true. Okay, so it's kind of what I just said. It's a series of true statements. Every statement here that you write down has to be true. And they logically progress to a final conclusion that you're trying to actually prove is true. Okay, so let's just do a quick example proof, something I think all of us can relate to. So here's an example. Prove that all students in geometry class will receive a grade between 0 and 100. Now this is an example of kind of what I was talking about here, about kind of something silly. I mean, I think you guys all know, right, that when you're in class you get graded, right? And when you get graded, you're getting graded on a scale from 0 to 100. And so logically, you don't even think about that. It's so simple. It's like, well, duh, everybody in class gets a grade. And everybody that gets a grade has a grade with these numbers. But that's what this proof is trying to get you to do. It's trying to get you to break down that logical thought process and write it down. Okay, and when we get, this is a silly example just to get the point across. Really, this has nothing to do with geometry. I'm just doing this to give you an example of what a proof is. But when we get to our geometry over here and actually looking at using our theorems that we've learned, then you will be using those facts to prove that something is true. Okay, so how are we going to do this? We're going to make one column called the statement column and one column called the reason column. And what we're going to do is we're going to prove something, and we're going to put what we think is true and why, and we're going to go all the way down to the conclusion. So the first thing is that students take geometry. Okay, and that's just given to you. Because really the problem says that students that take geometry get a grade, blah, blah, blah. Well, you're kind of given that the students are taking geometry, so you always start with the given. Okay, so this is the statement that we're claiming is true, and this is the reason why it is true. Okay, so the next logical piece of our puzzle is the students will get a grade in geometry. Will receive a grade in class. Okay, and the reason is that students of all classes get a grade. See, you're breaking this down into kind of these sort of absurd little statements of truth. Well, yeah, students get a grade. Okay, thank you very much. And the students will receive a grade in class. So first we're proving that the students will actually get a grade. And by the way, we're supposed to prove that they'll get a grade between this range and this range. And we're just saying that this is true because all students get a grade that take a class, okay? And this is just a truth. The student's grade will fall between 0 and 100. Okay? 0 and 100. And the reason is all grades are on a scale of 0 to 100. All grades that are ever given in class are from 0 to 100. So you see, we're building the building blocks, and so our conclusion statement is that all students will get a grade between 0 and 100. Okay? And this follows from everything that was above. since all students are graded, okay, and the grades, I'm kind of doing shorthand here to hurry up, grades are from 0 to 100, then that implies, as a conclusion, that all students get a grade between 0 and 100. So let's just think about this for a second and just go through it, because this kind of stuff is silly, but it's exactly what we're going to be doing for the next 20 or 30 minutes here. Okay. Prove all students in geometry class will get a grade between 0 and 100. Well, the first thing is we say students take geometry, given. That is just a fact, okay? Students will receive a grade in class, okay? That's something that you may not know. If maybe this class doesn't give grades, who knows? But this class does. Students of all classes receive a grade. Now you say the student's grade will fall between 0 and 100 because all grades are graded on a scale of 0 to 100. And then the final statement, all students will get a grade between 0 and 100. And then the final conclusion statement is that all students will get a grade between 0 and 100 in geometry class. Okay, it's kind of implied here in geometry class because of everything that's fallen above. All students are graded. The grades are between 0 and 100. Therefore, all students in geometry class will get a grade between 0 and 100. So this is just a silly example. Okay, it's just a silly example. It doesn't really, nothing to study here. Don't rewind it and play it again. But it illustrates the point. You're taking a statement and you're breaking it down into steps, and you're breaking it down into really simple steps, okay? And that's what we're going to be doing for the next period of time here. Now, what kind of statements would you use in your geometric proofs? Well, you've learned all kinds of very important statements that you're going to use in all of your proofs, okay? You know, for instance, think about everything we've learned in this course. You've learned things like there's 180 degrees in a triangle. That's a fact. You've learned there's 360 degrees in a circle. You've learned the formulas for lots of the volume and surface area of objects. You've learned about bisectors that split an angle into two parts. You've learned about perpendicular angles that are always 90 degrees. You've learned at parallel lines that never intersect. You've learned about all kinds of geometric principles that you're going to be able to use in your proofs. So you've kind of learned that, okay? And all of the books that in geometry actually have a whole list of all these other mathematical properties that are also important for your proofs. Now, I'm going to tell you some of the most important ones here that we're going to use as we go on and do our proofs. But I got to be honest with you, some of these, in fact, a lot of these mathematical statements I'm about to share with you here are very, very silly. I mean, you'll see what I'm talking about when we get here. They're so obvious that you would just think, why would you ever write them down, okay? Well, the truth is that the only way you progress in science and math is to take the known and make it really obvious, okay? And then move on and gradually expand and prove something that may not be obvious. So you can take a collection of obvious statements and put them together and prove something that may not be so obvious, okay? It's kind of like when I'm presenting these courses. I mean, I'm trying to decide what should I tell you and what should I not tell you? What is obvious to somebody and what is not obvious, okay? And trying to draw that line. Well, in math, you really want to make sure you're very, very obvious, okay? So that everybody understands what's going on. So let me go ahead and share with you, looks like there's maybe a dozen or so of these, maybe 10 or so of these mathematical statements. They're going to be very silly. They're going to be very easy to understand because I'm going to explain them to you. And then after that, we're going to actually work some proofs, you know, and we'll get a feeling for how to do that. Okay. The first one is called the reflexive property. You're going to laugh when you really see some of these. The reflexive postulate, I should say. Quantities, and I'm going to write it down and explain it to you, are equal to itself. Okay, so what this means is that literally it's exactly what it says. If you have a number or a variable z, it is equal to itself. So all this is saying is the number 3 is equal to 3, 4 is equal to 4, 17 is equal to 17, z is equal to z. Reflexive property just means something can be set equal to itself. Like I said, these are pretty simple. These are pretty simple, and you would wonder, why in the heck would you even put them in a book? They're that simple. Well, you have to start somewhere, and you have to make sure everybody knows the building blocks that you'll build your proofs on. So you have the reflexive postulate. Okay? The next one's the symmetric principle. Again, it's a simple thing. Any equality can be reversed. Okay, so what this means is if x equals y, then I can also say y is equal to x. See, it's another one of those big red truck duh moments. It's like, okay, x is equal to y, therefore y is equal to x. Okay, we've been doing that since, since you were very little. That's a symmetric principle. The third one is actually pretty interesting and maybe not quite so obvious, and that's very, very important. Transitive property. Okay, this one says, I'm just going to write this down in math. If A is equal to B and B is equal to C, then that implies that A is equal to C. Okay, this is the one that basically says, in words, if I give 2 pencils to Henry and Henry gives 2 pencils to Jane, then in the total sum of things, I have given 2 pencils to Jane. A is equal to B, B is equal to C, therefore A must also be equal to C. That's all it's saying. That's the transitive property. You'll probably use that one a few times. Here's the substitution property. Okay, substitution property. And that one basically just says that you can substitute values into equations. So let's say you have in math 2x plus 3y is equal to 10, and you also know that x is equal to 1. The substitution property just says that you can take this x and you can actually substitute it for its value. So you could write 2 times 1 plus 3y is equal to 10. And this is very valid because here you're using a symbol to represent the term x, and you know what x is equal to, and you can substitute that in. And by the way, as we go on here, a lot of these properties are going to be algebraic properties. I mean, like the substitution property, that's just from your algebra. You know that you can substitute things into equations if you know the value. And this is just writing it down. If you have to use that in a proof, you can state why it's legal what you're doing. But a lot of these are going to be, in fact, I think all of the rest of these are all going to be algebraic properties. So you have an addition rule. You have an addition rule, and I'm just going to write it down in math instead of in words. Your textbook will probably have a lot of words here, but I'd prefer to work with the math. If you have something like x plus 2 is equal to 4, the addition rule says that you can add the same number to both sides of an equation. And you already know this. You can do anything you want to both sides of an equation as long as you do it to both sides. So you could say x plus 2 plus 7 is equal to 4 plus 7 because I'm adding 7 to both sides. I could add 84 to both sides. Again, that's just algebra. But maybe you're working some proof where you need to do that, and you'll need to justify that the addition rule is what lets you do it. So the subtraction rule, I think you could probably guess, is exactly the same thing. Y minus 7 plus, let's say y minus 7 is equal to 2. I can subtract the same number from both sides as long as I do it to both sides. So I can subtract 1 on both sides of the equation, and I have a perfectly valid equality. So that's the subtraction rule. Now, there's going to be a multiplication and a division rule, and I think you can figure out what that is. It's the same thing. If you have a is equal to b, some equation, then 3a is equal to 3b. I can multiply both sides of this equation by the same number. That's just it. It's just algebra, but that's exactly what it says. And you have a division rule. Okay, it's the same thing. If I have x is equal to 2y, I can divide both sides by the same number. Here, I just divided the left by 3 and I divided the right by 3. This is all just coming from algebra. And the final thing I'm gonna share with you here is the root and power rule. Okay, and what that means for the root and the power rule, if let's just say I have an equation s is equal to t. What it says is I can take the square root of both sides. So I could take the square root of s, and I could take the square root of t, and then this equality is still true. And I could also raise both sides to some power. So I could raise this side to a power of 2 and this side to a power of 2, or I could raise it to a power of 3 or a power of 4 or whatever. Okay, so here you have some very simple rules that are kind of algebraic rules, and you've also got in your bag of tricks tons of theorems and side angle side and all these other things that we've talked about in this entire course, the geometric properties that you've learned that you can also apply to your proofs. So now let's go ahead and work some actual proofs, some problems, and figure out how we're going to actually do some of these. Okay, the first proof we're going to do, you're almost always going to be given some kind of figure for a proof. So here I have a triangle A, B, C, and there's also this vertical line in the triangle, and this point where it intersects is called D, and you'll be given something. You'll be given that BD in this problem is a bisector of AC. Okay, it's a bisector of AC, and you want to prove, so you have to have a very clear statement of what to prove, that AC is equal to 2DC. Okay, so you're given that this is a bisector of this, and you're trying to prove that AC is equal to 2 times DC. Okay, so how are you going to do that? Well, you have to have a statement, and you have to have a reason for that statement. So let's start at the very beginning. We're given, you always start with what's given. BD is a bisector of AC. Always write it down, even if it's obvious, even if it's written down right above it, always start with it, and you just write the word given right here, because you always start with what you're given, okay? So BD is a bisector of this guy here. So what does that mean? Okay, don't forget what we're trying to do is we're trying to prove that this quantity is equal to 2 times this quantity, okay? So you have to kind of have a plan of attack and go and logically prove that. And I think you can kind of see that it's true, because bisector means that it cuts it in two. This is a bisector. That means it cuts this thing in two. And if it cuts it in two, then certainly this distance is going to be 2 times this distance. We just have to prove it. So what does this bisector business mean? It means that AD, okay, this guy, is equal to DC. Okay, and the reason is because it's the definition of a segment bisector. And a bisector means you cut it in 2 parts, 2 equal parts, okay? And you have to do that because it's a logical thing, because you have to write that down so that you can actually start to prove that this is equal to 2 times that, okay? The next step in the chain is to figure out what is the relationship between these segments. Now, AC, which is the whole thing, is equal to AD plus A plus DC. AD plus DC. We haven't said anything about this 2DC business. All I'm saying is that this entire segment is equal to this plus this. And you can even use in your justification from figure. Okay? Next, we want to use a substitution, because notice we use the definition of the bisector to say that AD was equal to DC. So now we can say that AC is equal to, and we can plug this in, DC plus DC, okay? So we substituted what we actually found in the first step into what we found in the second step. So I think I already gave you the answer there. We used substitution. And what we substituted was AD is equal to DC. So we actually put that in here. And then 5 AC is equal to 2 DC. And that's just because DC plus DC is 2 DC. So that's just a simplification. Okay? So here we have our first proof. Okay? You're given this guy. You start with a given and you want to prove this, and you just have to logically go through it. First, you say, well, this is a bisector, so this is what I'm given. Bisector means that I cut this segment into equal parts, so AD is equal to DC. AD is equal to DC. Next, I'm starting to work towards my conclusion. I say that AC is equal to AD plus DC. AD plus DC, okay, from the figure, okay? And then I substitute what I found before into here. So AC is DC plus DC. By substitution, you have to justify it. This is that mathematical substitution. And then you just simplify that and you can get to the proven answer, and then you stop because you've already made your proof. You've already made your proof. Okay, our next proof is going to have a figure like this. Okay. This is A, this is B, this is C, and this is D. And you're given that AC is perpendicular to BD. Perpendicular to BD, okay? And you want to prove that angle DBA is a right angle. So here you're given that this is perpendicular to this, and you want to prove that DBA is a right angle. So it seems, I mean, you know, just even by just looking at this, it looks pretty simple, because you know that the definition of perpendicular angle is 90 degrees, and 90 degrees is a right angle, but you have to actually write that down mathematically. So you have to get your statements and your reason. And you have, even though it may seem simple, you have to go step by step and make sure everything makes total sense. So you always start with your given. So AD is perpendicular to BD, and that's given. Okay? Given. Now the next thing you want to do is you want to use what you were given and you want to build on it. So we're going to say that the measure of angle DBA is 90 degrees. And this is because the definition of perpendicular lines, specifically perpendicular lines, are 90 degrees to one another. So then you can prove that this angle is 90 degrees because this is perpendicular to this, so this must be 90. So then 3, you want to look and you want to say right angles equal 90 degrees. And this is just the definition of a right angle. Okay? So you're making a logical progression. These are perpendicular, so this angle's 90. Now right angles are 90 degrees. So what do you think the fourth statement is just going to be the conclusion statement? So the final conclusion step is that angle DBA is a right angle, and you're using the fact of substitution here because you started from the beginning saying these are perpendicular, and because of that saying this angle is 90 degrees, and saying that all right angles are 90 degrees. So by using this, by substituting in and saying, well, if this is 90 degrees and all right angles are 90 degrees, by substitution, you can say that this angle therefore must be a right angle. Okay, our third proof is I'm going to be given an angle here. Okay, and this angle is going to be called A, and I'm going to be given another angle here, and this angle is going to be called B, and I'm going to be given that the measure of angle A is 20 degrees, and the measure of angle B is equal to 20 degrees, and you're going to prove that the measure of angle A is equal to the measure of angle B. Now you may think this is pretty simple. I mean, in fact, it is simple. This angle is 20 degrees and this angle is 20 degrees. Prove that they're equal to one another. Well, it's true, but on a test, you can't just say this is true. You have to actually prove it. So statement and reason. Okay, statement and reason. Okay, so first start with your given. The measure of angle A is equal to 20 degrees. And that's given. Measure of angle B is equal to 20 degrees, and that's also given. So use your givens. Now, what am I going to do now that I've got my givens down? Well, now I'm going to go ahead and make my conclusion. The measure of angle A is equal to the measure of angle B. What property can I use to define this? Well, if A is equal to B and B is equal to C, then A is equal to C. So I'm going to say this is the transitive property. Remember, what transitive meant was if A is equal to B and B is equal to C, then A is equal to C. And what you're saying is this angle is equal to 20, where 20 would kind of be like B here, and 20 is equal to the third angle. So then the first two angles must be the same because they're equal to something in common. That's what it means. That's what the transitive property is really saying. If two things are equal to some common thing, then they must be equal to each other. And it's an obvious thing, but it's absolutely true. So this was a simple one, but you see, you have to have these steps written out or you're just not going to get the problem right. Let's do one that's a little bit more complicated. Let's say you have a figure that looks like this. Okay. Okay, I've got a bunch of rays here. And this is K, and this is Q, and this is L, and this is M, and this is N, and this is P. So here's your figure, okay? And what you're given, is a QL bisects angle KQM. And QN bisects MQP. Angle MQP. So what you're saying here is that QL, this one, bisects KQM, this angle right here. So this bisects this. And QN bisects MQP, this angle right here. Okay? So now you want to prove, in fact, I'm going to go ahead and write this down right here. You want to prove that the measure of angle KQL plus the measure of angle NQP is equal to the measure of angle LQN. So what you're really trying to prove here is that KQL, this angle here, plus NQP, okay, is equal to LQN, which is this bigger angle here. So this angle here plus this angle here gives me this big giant angle here. That's what I'm trying to prove. And all you're given is that you have some bisectors here. So let's just take it one step at a time. And we'll do our statements and our reasons, and we'll just take it one step at a time, and we'll work from the beginning and we'll make our way to the end. Okay, so first we start with the givens. Always start with the givens. QL bisects angle KQM. QL bisects KQM. That's a given, okay? So we'll just write that down, given. Okay. Now, what does this mean? Okay, let's go ahead and just figure out what this means first. This means that if it's a bisector, this angle is equal to this angle because it cuts it in two. That's what a bisector does. So the measure of angle KQL must be equal to the measure of angle LQM. And that's just the definition of a bisector. So here we're starting to do some math. You see, because we've used the bisector to show that this angle is congruent to this angle up there. And that's just true because it's a bisector. So you want to write that down. Now let's go back up the truck a little bit to our other given, to our other bisector. QN bisects angle MQP. And that was given. So we just write that down, given. We want to work with both of our givens, and we're going to do the same thing here. We're going to say this splits those angles up there just because it's a bisector. So the measure of angle MQN must be equal to the measure of angle NQP. And again, that's just the definition of angle bisector. Okay, these two angles, this angle here must be equal to this angle here just simply because it's a bisector. So you could say that this angle, put a double mark, is congruent to that one there, equal to that one. Okay, now what are we trying to prove? we're trying to figure out an expression for this angle, LQN. So let's write that down. The measure of angle LQN, what would it be equal to? It's equal to this one plus this one, right? Just by looking at the drawing. So that's equal to the measure of angle LQM plus the measure of angle MQN. All we've said is the angle we're trying to actually find an expression for, this one, is equal to this angle plus this angle. Okay, LQN plus MQN. And I can't number here, so this is 5. And the definition here is from the figure. And you can also say angle addition. And what this is really saying is that the sum of two angles is equal to the larger angle. Okay? Okay, now that you have an expression for what you're trying to find, let's go ahead and substitute in what we have found before, because notice we have some expressions that will work here. So the measure of angle LQN is equal to, let's look at this one. LQM we found is equal to this. So we'll just plug that in. KQL plus. And then over here, MQN, we have an expression for that. Measure of angle NQP. And that's from substitution. Okay, because I had an expression and I just plugged in what we had already found. And that is actually exactly what we want to prove. LQN is equal to the measure of angle KQL plus NQP. Sorry, that should be NQP. Okay, and so what we did is we started from the beginning that we had a bisector that was given to us. So we knew that these two angles had to be the same, and we showed that. The other bisector had, these two angles had to be the same, and we showed that. And then we wrote an expression for what we were actually trying to find, which is this angle here was the sum of this angle plus this angle. And then we just substituted in what we found to arrive at that answer. Okay, next proof we're going to do is going to have a drawing like this. You have a triangle, A, B, C, and you're given that this is congruent to this. That side's congruent to that one. And so you're given triangle ABC from the figure, and you're given that AB is congruent to BC, which is also given in the figure. AB is congruent to BC, and you want to prove that angle B is congruent to angle C. This angle is congruent to this angle, so you just want to prove that. So the next thing we're going to do is, and you'll see why we're going to do this here in a second, is we're going to draw a bisector down here. Now that wasn't given to us, but I'm going to draw it myself in a different color. And you'll see why here in a second. Draw that bisector and put an X down there. And we're going to use that here in a second as we go forward. This one's a little bit tricky, so we have to draw this bisector here. And we're basically splitting this big triangle into two smaller triangles. Okay? So let's write, and it's a bisector, our statement and our reasons. And remember, we're just trying to prove that those two angles are the same. Okay, so AB is equal to BC. That's just given. We just always start there. Okay, now 2. We're going to draw in our figure that AX bisects angle CAB. CAB bisects this angle. Okay, and what we're going to say here, this is the definition of a bisector. Okay, angles have only one bisector. So here I'm just putting it in the proof mainly because I'm just showing, you know, if I were going to show this for the teacher, I need to show them that I drew something called AX. It is a bisector. Angles only have one bisector. That's why there's only one line there. Okay. Now, here's your chance to use this goofy thing called the reflexive property. AX is congruent to itself. AX, let me explain why. What I'm doing here in the big picture is I'm drawing this bisector because I'm going to end up using this little bitty triangle here and this little bitty triangle here, and I'm going to end up using some properties to prove that these angles are the same. In order to do that, since I've got two separate triangles now that share a common border, it's important to just spell out that AX is equal to itself, basically, because I'm going to end up having two triangles and I'm going to share a common border there. And so that's why you have that there. Okay, so let me just get through the proof and we'll go back over and make sure every step is understood, but we need to kind of keep moving because the momentum will be lost if I continue to talk about one thing forever and ever, okay? Angle CAX, okay, is congruent to angle XAB. Because this is a bisector, CAX, this angle right here, is now congruent to this angle right here. So I can actually draw that. This is congruent to this, that those angles are the same angle, okay? Now, why is that? That's a definition of the bisector that I just drew myself. And by the way, you can do anything you want to this drawing as long as it's legal. If it helps you prove it, you can do it. Okay? Now, I'm going to make a leap of faith here. Triangle CAX is congruent to triangle BAX. What I'm saying is CAX, this triangle, is congruent to BAX. That means they are the same exact triangle. They look exactly the same. And they are the same size and they are the same shape. And the reason is, you always have to have a reason, side, angle, side postulate of triangle congruency. This side, this angle, and this side are congruent to this side, this angle, and this side. Side, angle, side. Because this is a common border, it's congruent to itself. That's why I needed to write this down to make it clear that this was congruent to itself, because that was going to be important later on for the side, angle, side postulate, because the sides have to be congruent. So you have to prove that the side is, this side is also the side of this triangle, and this line is also the side of this triangle. So you have to prove and just show that they're the same thing in order to use them. And then finally, the conclusion statement, the measure of angle C is congruent to the measure of angle B. And the reason that's true is because corresponding parts of congruent triangles are congruent. Okay, corresponding parts of congruent triangles are congruent. What that means is, here I have two identical triangles, and so that means the corresponding angles must be the same, the corresponding sides must be the same. And so angle C is equal to angle B because of that. So just starting from the top, given this picture, starting from the top, AB was equal to BC, okay, that was given. I drew a bisector and split this angle up in two because I have only one bisector there. And because of that, this side was congruent to itself because of the reflexive property, and I only needed that because later I was going to use this side in the proof in two different triangles. So I needed to show that that side was the same, so I could use the side angle side postulate later on. Now this angle is the same as this angle up here because of the bisector, definition of the bisector, and that was going to be important later on. And then I proved that this triangle CAX is the same as this triangle BAX, because of the side angle side postulate being congruent to this side, this angle, and this side. And then the corresponding parts of the congruent triangles are always congruent. So you can see there that there's a lot of steps here, but you started one at a time. You started with the path, and when you do your proofs, you're probably going to start down many paths. And you'll go down there and you'll say, well, that isn't really working out. I'll have to back up the truck and try something a little bit different. Okay, try some unique things. Try to add things to the drawing that make sense, that help you prove what you need to prove. And the final thing I want to say is there's no one right way to do a proof. It's more like art than solving an equation. You see, solve an equation, there's really only one way to go about doing it, or at least the simple algebraic equations. When you start getting into complicated math like geometry and even physics and calculus and things like that, you get into subjects where there's no right path to the end. It's just as long as you can justify your steps and your steps make sense, then the answer is correct. So in this case, I chose a path and you may choose a different path. And as long as your steps make sense from one to the other and they're defensible and they're justifiable, then as long as you get to the end and you get to the right conclusion logically, you're doing the right thing. And there's a good introduction of proofs in geometry.
learn anything at mathandscience.com.